Welcome to tutorial number 3 on enzyme kinetics. So today we will start with question number 4, which asks you to derive the equation for uncompetitive inhibition. Yes, this is the double reciprocal form of the equation for uncompetitive inhibition. So in order to derive, we first need to write the schematics for the enzyme inhibition. So this is the schematics where enzyme substrate complex ES is forming ESI reversibly, and therefore this doesn't give you the product, but ES gives you the product following K3. So therefore the velocity of the reaction or the enzyme catalysis is expressed by this equation, and we have to remember that at any time point the total initial enzyme concentration should be equal to this. Okay, and so we have to apply the concept of steady state, and it is applied on the two intermediates, ESI and ES. So let's start it on ESI. So we can write dESI dt is equal to, so from here we can get that K1 double prime ES multiplied by I minus K2 double prime ESI. Okay, and according to steady state approximation we can put this is equal to 0. So then this gives us the value for ESI also. The concentration of ESI then becomes K1 double prime divided by K2 double prime multiplied by ES multiplied by E. And now we are going to write the expression for DES dt, another intermediate. So that should be equal to K1 ES, okay, minus K2 ES minus K3 ES, and then of course we have minus K1 double prime ES multiplied by I, right, and minus K2 double prime, sorry, plus K2 double prime ESI, isn't it? Okay, so therefore the steady state approximation demands that this equation is equal to 0. So therefore what we get, now let's take a look at this expression. So this is already equal to 0. So if I take this minus part common, then this becomes minus. So this part has already been determined to be 0. So therefore from this what we can get that, or from this part we can write that K1 E multiplied by S is equal to ES multiplied by K2 plus K3, and therefore we can find an expression for ES. So therefore ES becomes equal to E multiplied by S and divided by, we can write this in this form because we know that the denominator we just have written, this is the Michaelis constant Km. So following this we can replace the value of ES over here. So this becomes K1 double prime divided by K2 double prime, and instead of ES we can write E multiplied by S divided by Km and multiplied by I. Okay, so therefore we now, our goal is to find a solve for the enzyme concentration E, which is unknown at any time, in terms of some known quantities. So the known quantity probably E naught, so we have to express that in terms of E naught. So doing that, we need to find the value through these expressions ES and also ESI. So therefore what we are going to do, that we are going to put these two values, ES and ESI, in this equation, and we'll try to solve, or we'll try to find the value of E. Alright, so let's clean the board and do it. Okay, so before we begin, I apologize for a mistake. So the E naught, the total enzyme concentration we started with, it should be any unreacted enzyme E plus enzyme present in the enzyme substrate complex ES and enzyme substrate inhibitor complex ESI. So before, by mistake, I have written EI. So just pardon me, it should be ES. Okay, so this is the correct expression. So now therefore, what we are going to do is, these are the values for ES and ESI. We have just now derived this. So we are going to plug in these two values over here. Okay, so therefore we have a term E over here and also E over here. So I'm going to take the E part common. So if we take E common, so we have 1 plus, instead of ES, we have S divided by Km plus, instead of ESI, we have K1 double prime divided by K2 double prime multiplied by S multiplied by E divided by Km. Alright, so and bracket closes. So from this, you see, now we can easily find the expression for E. So expression for E becomes E naught divided by 1 plus S divided by Km plus K1 double prime divided by K2 double prime multiplied by S multiplied by I and whole divided by Km. Alright, so now you see that this value E is now expressed in terms of measurable quantities. Okay, so now let's try to find the velocity value V. So V is equal to K3 multiplied by ES. And what is the value of ES? So we are going to replace the value of ES, whatever we have found so far, by applying steady state approximation. So this becomes ES. So this becomes, if this becomes ES, then simply we have to plug in the value of E from here. So therefore it becomes K3 multiplied by E naught multiplied by S divided by, now we have this denominator and now also we have this Kn. So now I'm writing it one step by multiplying Kn with this value under the bracket. So we get Kn plus S plus K1 double prime divided by K2 double prime S multiplied by I. Alright, and therefore we can further simplify this equation, and this is how we can simplify it. So therefore what I'm going to do, I'm going to simplify on this left hand side, and this is equal to my V, so I'm going to write V over here. So if I want to simplify, so you see K3 E naught is equal to V max. So this becomes my V max multiplied by S, now divided by Kn plus, if I take S common, then it becomes 1 plus K1 double prime divided by K2 double prime multiplied by inhibitor concentration. Now this constant quantity means apparently constant because this is dependent on the inhibitor concentration I. So this is this can be called as alpha prime. So therefore this becomes V max multiplied by S divided by Kn plus S multiplied by alpha prime. So and this is equal to V. So that's how we get the Michaelis equation for the uncompetitive inhibition. Okay, so now we have to take the double reciprocal plot. So if we take the double reciprocal plot here, so what we get, that 1 over V is equal to what we get here first, S cancels out, so alpha prime divided by V max, alright, plus we get Km divided by Vmax multiplied by 1 over S. So this is the Lineweaver-Burke form of uncompetitive inhibition, and we have derived and proved this way. So remember, this is a very critical derivation. So you must practice it out so that you can show this derivation in exam if the question comes. So now we move on to the next tutorial question. So next we go to question number 5. So question number 5 was a similar question. You have to derive the equation for mixed inhibition, the Lineweaver-Burke form. So here we have two terms, alpha and alpha prime. So where alpha is defined like this and alpha prime is defined like this. So therefore we have to go through exactly the same operation. That means first we have to write the scheme. So here mixed inhibition means both competitive and uncompetitive going simultaneously. So this is the competitive inhibition forming EI, which is the uncompetitive inhibition forming ESI. So therefore, we have to follow the same practice. V is equal to K3 ES and E naught is equal to, it is the summation of 4 terms, E, ES, EI and ESI. Alright? And therefore, now we have the 3 intermediates now. So 1, 2 and 3. Okay? So therefore, we have to apply the steady state approximation for these 3 terms. So we have dESI dt is equal to 0, we have dEI dt is equal to 0, and therefore we have dES dt is equal to 0. So like question number 4, we have to apply the same thing here, but just for an additional term. So the trick is, we should apply, we should derive dESI dt is equal to 0 first, and then on dEI dt is equal to 0 second, and at the end we should find out the largest expression, that is dES dt is equal to 0, and then by following the exact same procedure we need to find out the expression for E in terms of some measurable quantities, that is E naught and something else, and therefore finally if we find that E expression for E, then you have to put it here, and then if you solve it and then you take the double reciprocal, then you will be arriving at this form. Okay, so this is just some more exercise, and I have shown you or told you how to do it. So it's your job, so please try it and verify you have successfully reached at this final step. Okay, so just do it yourself. So now let's move on to the next question. So now we come to question number 1. So it says, draw velocity versus S plot for increasing inhibitor concentration in case of competitive inhibition. So for competitive inhibition, what happens is that Vmax remains unchanged. So no change. Vmax is constant with respect to increasing I. And then the apparent Km, so the apparent Km is also known as Km prime, can be expressed as Km multiplied by alpha. So now alpha contains the I term, so with increasing I, so this alpha term increases, so therefore the apparent Km prime increases. Okay, so therefore we just need these two information, Vmax unchanged and with increasing Km prime with increasing I. So with that we can draw the velocity versus S plot. So this is the S axis at the X and V axis at the Y axis. So first let's define the Vmax. So this is our maximal velocity line, and then we assume that is the inhibitor free, so no the V versus S plot for an uninhibited kinetic. So the graph plot, as we have seen earlier in the lectures, let's assume that it follows this way, this curve. And according to that, what is our Km? So Km should be Vmax by 2. So it is the substrate concentration at Vmax by 2. So this is the Km. Alright. So here we have no inhibition, right? So now we have increasing inhibition concentration. So it says the Vmax is unchanged. So for the new plot that I'm going to draw, it should reach to Vmax. But the hint is the Kmax or Km, sorry, the Km prime increases. So how are we going to draw it? So therefore, if Km increases means that when Vmax is changed, so Vmax is divided by 2. So this line should be somewhere here, and in that case, we can assume that this is our Km prime. All right. So therefore, we have to draw the V versus S curve, something like that. There you go. So this is our Km prime. So we can say that Km prime is greater than Km, and in this case, if we call this is I2 and this is I1, so definitely I2 is greater than I1. So therefore, we can also draw subsequent lines for further increased inhibitor concentration. So therefore, suppose if we have a further Km double prime right over here, so Km double prime, and then we have to draw the velocity versus S curve, something like that, and it would reach to the Vmax at a very far, at a very, very high concentration of substrate. So I'm not drawing it here. So it would reach up something like there. Anyway, so this is the solution for the question number 1. So I hope you have understood. So let's move on to the next question. So the next question says, draw velocity versus S plot for increasing I in case of uncompetitive inhibition. So once again, before we proceed to draw, we have to understand two things: how Vmax and our Km, or apparent Vmax and apparent Km, changes with respect to increasing I. So for the ease of understanding, I have placed the Lineweaver-Burke form for uncompetitive inhibition. So here you can say that apparent Vmax can be found out to be Vmax divided by alpha prime, and alpha prime contains I terms, so with increasing I, the denominator increases. That means the apparent Vmax decreases. So we can write the apparent Vmax decreases with increasing I. All right. So now the question is, what would happen to the apparent Km? Okay, so that's the question. So from here, it may not be very obvious what would happen to the apparent Km from this equation, right, in this manner. But if you recall the line, so if we recall the Lineweaver-Burke form, when we plot 1 over S versus 1 over V, obviously we used to get a straight line for an uninhibited case. And the intercept here is actually minus 1 over Km. So from this we can also find the value of Km. So let's try to see what happens for the apparent Km. So you will reach this value whenever the 1 over velocity value becomes 0. So we have to find what is the value of 1 over S for 1 over V is equal to 0. So from this we can write that at this point 0 is equal to alpha prime divided by Vmax plus Km divided by Vmax multiplied by 1 over S. Or therefore we can write minus alpha prime is equal to Km divided by S. Alright. Or from here, okay, so we can try to get that the value of S is nothing but minus Km divided by alpha prime. So this one, obviously, from this we can get that for uninhibited reaction, S is equal to minus Km. So now whatever we get, S is equal to minus Km by alpha prime. So in this case, the apparent Michael is constant, Km becomes Km divided by alpha prime. Once again, like Vmax, with increasing value of I, alpha prime increases and therefore the apparent Km value decreases. Okay, so we can then write the apparent Km value decreases with increasing I. So finally, we arrive at the conclusion that for an uncompetitive inhibition, both apparent Vmax and apparent Km, these two decreases, okay, with increasing I. So now we have to draw the velocity versus S plot. So this is S, substrate concentration, and this is V. So first we draw the uninhibited case. So this is my Vmax, and we are going to draw the graph plot exactly like this. Okay. And my Km for this is Vmax by 2, and the intercept on S-axis is, this is the Km, uninhibited, or very lower value of Km, lower value of So I'm now going to draw the same graph with increasing I. So when I increases, apparent Vmax decreases. So let's try to draw a line here for Vmax prime. Okay, so obviously Vmax prime is less than Vmax. So now what would happen for the apparent Km? So now it says the apparent Km decreases. So therefore this is the Km and this is the Vmax by prime. So half of that, so Vmax by prime value, half of that would be around here. And then if Km decreases, so at the decreased value we can pick up that value. So if we draw a plot like that, so the intersection of two lines would come over here. So now it gives us a way to plot the V versus S curve. So that curve will go like this and it will saturate somewhere over here. So therefore this is the Km prime. So here, so this Km prime signifies that this is Km divided by alpha. So with increasing alpha value, consequentially Km prime value would keep on decreasing. Alright, so definitely here Km prime is less than Km. Alright, and also Vmax prime is less than Vmax. So this is how the V versus S plot goes for an increasing concentration of I for uncompetitive inhibition. So let's move on to the next question. Question number 3. So the next question was that in uncompetitive inhibition, what happens to the apparent Vmax, apparent Michael is constant, and the velocity with increasing I? So this is the question we just solved while answering how to plot V versus S plot for increasing inhibitor concentration for uncompetitive inhibition. So simply the answer is Vmax apparent decreases, Km apparent decreases, and obviously velocity would decrease. So you can verify that from the double reciprocal plot of uncompetitive inhibition. So you will see that the 1 over V lines would gradually get shifted towards the higher value of 1 over V axis. So that means the velocity decreases. All right. So next move on to let's move on to the next question. So we begin question number 6. Question number 6 says that if this is the equation for mixed inhibition, and then in a very special, although very rare case, if alpha becomes alpha prime, then we get a unique case. It's called non-competitive inhibition. So the question is, draw both the Lineweaver-Burke and V versus S plot for this unique situation of non-competitive inhibitions. Okay, so far we had competitive inhibition, uncompetitive inhibition. Now there's a new term, it's called non-competitive inhibition, when alpha is equal to alpha prime. Okay, and it happens by chance. Okay, the thing is how to draw the plot. So once again we go to the basics, that we need to know the two variables, how it changes with increasing I. One is Vmax and another is Km, or apparent Vmax and apparent Km. So if we see by looking at the equation, that apparent Vmax here is actually, I'm sorry the microphone was not connected. I hope now you understand. So the apparent Vmax is now Vmax divided by alpha prime, which is equal to alpha. So in any case, in any way, with increasing I, the Vmax or apparent Vmax will increase. It is very obvious from this equation. Now the question is, what would be the expression for apparent Km? All right, although this is not very clear from here. So how we get the value of apparent Km? So once again, we take this equation and we will do the same thing as we have done it for the uncompetitive inhibition. That is, we will put 1 over V is equal to 0 and we will try to solve for S value. Okay, and that will give us the value for Km. So if we do that, here alpha is equal to alpha prime, so these two cancel out. So finally, we get S is equal to minus Km from this equation. So that means here the apparent Km is devoid of, it does not contain any alpha or alpha prime value. So therefore the apparent Km is constant. So the answer is the apparent Km does not change with increasing I. So we are going to draw the both Lineweaver-Burk and V versus S plot with these two pieces of information. So let's clean the board and draw it. Okay, so let's try to draw it here. Let's first try V versus S plot. So for uninhibited kinetics, so let's assume that this is our V versus S plot. And so here it gets calculated at Vmax. And Vmax divided by 2, so right around here, so this point is the uninhibited Km. Alright. So now we have some increased inhibitor concentration, and therefore now we know that the Vmax, apparent Vmax decreases. So let's assume that this is the new Vmax and we call it the Vmax prime. Okay, it decreased. But at the same time, we have to remember that the Km remains constant. It's a very unusual thing, but it happens. So for that, how we are going to draw? So Km remains constant means, so Vmax, half of the Vmax by prime, Vmax by 2, so we have to take the half value here. So and then, so that should come to somewhere at this point. So this is the same Km as the previous one. So now we have to draw the graph plot. So therefore, with this point and connecting that point, the new graph would look like something like this. All right, and then again we can suppose we can draw another thing, Vmax double prime with enhanced inhibitor concentration divided by 2. We have the Vmax by 2 value over here, but Km remains constant. So here again we have the new point there. So for the third plot, the plot something goes like that. Okay, so that is Vmax double prime. So here I have, we can write that I have I3, I have I2, I have I1. So here the situation is I3 greater than I2 greater than I1, but Km remains constant, and you see the apparent Vmax decreases. Now we have to reciprocate that for a double reciprocal plot. So Km remains constant. Okay, so this is the point. Okay, and we call it minus 1 over Km, and it remains constant. But Vmax, apparent Vmax decreases, that means 1 over Vmax increases. So let's first draw a line for uninhibited reaction. So this is 1 over Vmax. Alright? And therefore, there should be another point for 1 over Vmax prime and another point for 1 over Vmax double prime. Okay? So now we are going to draw the plots. So remember, this is the point for fixed Km, and these are the new points, and obviously the slope would increase and our graph plots should look something, it will be even steeper. Okay, so yes, it will be even steeper like that. And once again, this is I1, this is I2, and this is I3, and the same relationship continues, that I3 divided by I2 and divided by I1, and you see with different intercepts on 1 over V axis with increasing slope. Alright, so this is for the non-competitive inhibition. Okay, and so now we go to the next question, that is our last question, question number 7. So now we come to our last question, question number 7. It asks that what happens for apparent Km and apparent Vmax and velocity for non-competitive inhibition, and answer the same for the mixed inhibition. So I believe that based on the discussion so far we had today, we have already seen the answers before. So, but once again, to answer this for non-competitive inhibition, we have seen apparent Km remains constant, apparent Vmax decreases, and obviously the velocity for non-competitive inhibition would decrease, because we have seen that 1 over the plots would be getting steeper and steeper. So that means the velocity decreases. And answer the same for the mixed inhibition. So did we answer the thing for the mixed inhibition, or do you have some doubts? Anyway, in order to remember all these parameters, so now things have become a bit complicated. We have no inhibition, competitive, uncompetitive, mixed, and non-competitive inhibition. We have so many parameters, that apparent Vmax and apparent Km. So sometimes it gets confusing for us to remember, but if we try to write that in a systematic manner, it may help you to remember the overall scenario. So let's delete this part and let's refer to a chart that I'm going to draw on the board. Okay, so let's do it. So here we go. I have written a summarized form of all these parameters with respect to different inhibition mechanisms. So when there is no inhibitor, apparent Vmax is Vmax and apparent Km is Km. And then for competitive inhibition, apparent Vmax remains unchanged and Km becomes alpha Km. So with increasing I, so whatever it is, that with increasing I, so we can write that it increases. So I'm just going to write I here. So that means apparent Km increases. For uncompetitive inhibition, once again, the apparent Vmax increases with, decreases, right? Yes. Because alpha prime would increase in denominator with increasing I. So I write D. And therefore also apparent Km decreases, isn't it? And for mixed inhibition, once again, the same thing here, it decreases. Okay, so we'll come to that later. And for non-competitive inhibition, again, the apparent Vmax decreases because alpha is equal to alpha prime, or alpha, either alpha or alpha prime would increase. So therefore it would decrease. And this Km remains unchanged. So if it's unchanged, we write U. Okay, so here also Vmax unchanged and Km unchanged. So now what is the question? The question is, what happens for alpha Km divided by alpha prime? So here it cannot be predicted. Okay, so because whether apparent Km would increase or decrease, that would solely depend on the ratio of alpha by alpha prime. So it cannot be predicted unless we don't know the value of alpha and alpha prime. Otherwise, with increasing concentration of I, we can predict all other apparent Vmax and apparent Kms from this chart. Okay, so this is all about the tutorials for enzyme kinetics tutorial 3. So I hope you are able to understand it. So please try to solve your own, and I will see you in our next tutorial. Okay, so till then, goodbye.